Thank you, Dan. I'm a professor in food engineering, associated with biological systems engineering. At Washington State, we have two departments involved in food research. One is food science department, and then biological system engineering. In the biological system engineering, we have about 3 faculties work on food engineering area. So my area is advanced thermal processing. Today, we're going to talk about microwave. Excuse me, I forgot to switch this on. A microwave and RF sterilization technology for packaged food. You heard about presentation yesterday, microwave sterilization of liquid products, aseptic processing. So here we're talking about packaged products. The project was supported by a lot of organizations, specifically U.S. Army Natick Soldier Center, and then later on USDA Emerging Technology Program. So we're going to have a meeting for the USDA program tomorrow. So hopefully I know how to use this slide. Here's the outline of my presentation. First, justification. Why do we want to look into new advanced thermal processing technologies? I'm going to list some limitations of a current technology that started about 200 years ago. Then we'll give a general description of what we are looking at and what's the potential. Then talk about dietary property of food related to microwave and RF. I'm going to very briefly talk about it. Of course, secondly, I'm going to talk about the industrial systems that are currently used for microwave sterilization, then to dietary properties. I'm going to go through the progresses that made mostly on the microwave and then RF. I focus on microwave because it is a major effort between Washington State University, U.S. Army Natick Soldier Center, and several companies that are working together. And we've been in contact with FDA over the last 2 years. And what we hope is to get this process approved by FDA in a time frame of 1.5 years or 2 years. The canning industry really started about 200 years ago with an invention by this individual, Nicolas Appert. At that time, French army need a long shelf life products to support invasion of Russia at the time. And then this gentleman bottled products in a whiskey bottle and then cook it in boiling water for 6 hours, and then the products was able to retain the quality without spoilage over extended period of time. Actually, if you look at the fundamental principles of what we're doing now in the canning industry, there's no difference from what they did about 200 years ago. It's basically using a heating media, hot water or steam to cook your product, and then to kill the spores inside. So this is a kind of shows what happens in the retort. This is a canned solid product. You use the steam or pressurized water at 120 degrees C or 250 Fahrenheit above, and heat the product, the surface product. The thermal energy migrate into the center, and that's the cold spot. What we try to do is to kill the Clostridium botulinum spores. It takes about 2 or 3 minutes to have a 12 log reduction at 250 Fahrenheit. But the problem here is that the cold spot this is the cold spot in the geographic center of the solid product, and that distance takes quite a bit of time for the energy to travel, to move, to raise the temperature, and depending on the size of the can, it may take 30 minutes, may take 2 hours, depending upon the size of the can. And as a result of that, you overcook the surface of the product, even though the center part is still good. But you open up the can, you can smell it, and then you can see the color changes. Now, what's the fundamental differences? What we're doing is instead of heating the surface, we applied energy into the center or the volumetric part of it, and then agitate the molecules of products and generate heat inside. So what process we can reduce the heating time. When we talk about microwave and RF, it's actually a part of the electromagnetic spectrums that we use every day when you use a cell phone, when you take airplane, it's a radar system that guide the landing of airplane is a part of the spectrum. But microwave is a little bit shorter wave. Has shorter wavelengths than RF. So the microwave is somewhere here, and RF is a longer wave. So on spectrum, microwave, we're talking about 300 megahertz to about 3 gigahertz, 3,000 megahertz. And RF, we're talking about 10 megahertz to about 200, 100 megahertz. But we are not supposed to use any frequencies in that range. Federal Commission, Communication Commission only allocated a few frequencies for us to use for industrial, scientific, and medical applications. We call it ISM applications because otherwise you interfere with the communication, we interfere with the landing system. So there are 3 frequencies that are allocated for RF, radio frequency application, 40.68, 27.12, and 13.56. And then give a bandwidth so that you have to stay in that bandwidth when you use industrial systems. So if you look at the wavelengths of these frequencies, it changes from 7.4 meters, that's one wave, complete wave, to 22 meters. So that's quite a long distance. Compared to microwave, microwave you use at home, a domestic oven is a 0.12 meters long, that much distance, less wavelengths. This 2450 megahertz is used at home in domestic ovens. I can talk about the limitation of that. And the advantage of that short wavelengths is you can design a small machine so you can have multiple wavelengths inside the cavity so that you can turn the food around and get a relative uniformity in there. The problem is the shallow penetration depths. So if you have a large food in there, it only penetrates a certain amount. So for industry applications, especially when you heat a larger body of products, we tend to use 915 megahertz system, which has 33 centimeters of wavelengths. So this is the generator, a 5 kilowatt generator of 915 in our lab. Imagine if you use this for home, they're going to take too much of your kitchen space. So we use it for industrial most of the time. But we do use the 2450 in industry. Basically, you use a lot of magnetrons, about 1 kilowatts each, and use 30 or 100 of them, and then zoom it into a cavity. So you can use that as well. So both frequencies are frequently used in the industry, depend upon the requirement of your application. For industrial microwave systems, this is you have a generator, and then you have a waveguide that lead the wave from the generator to we call it a cavity, and then you can design it as a continuous system with certain preventions at the entry and exit of the system to prevent the leakage of these microwaves, to ensure that there's the exposure is limited below the FDA limitation. So then you can use a continuous belt system to move the food around. So this is the APV system where they use microwave to do the browning, pre-cooking of meat patties. RF system is very much like an old-fashioned radio system used about 50s, 40s. Then you put, this is the vacuum tube, here, and this is a generation system here, power generation. Then you couple energy through these inductors into this part. And then what you see is a two capacitor, two metal plates, and then you can put food in between the metal plates, and then you tune it, just like an old-fashioned radio system. You basically change the capacitor to make sure that energy is coupled into the food. There's no direct contact of the food and then the electrodes. So therefore, you can pre-package a product. As long as it's not sealed metal container, you can use aluminum foil as lid stock, but still the energy can be directly coupled into the food without contact. So that gives you quite a bit of advantage in producing heating products at larger size. So the pilot plant unit that at Washington State University, what you see is that we took the cavity, the pressurized vessel out, and then you see the top electrodes and the bottom electrodes, basically the base of this cavity, and then we have inductance here. So this the top electrodes can be changed, adjusted. So if you put a food in between, you can tune it depending upon the size of it. RF has been used in the industry quite a bit for drying purpose, especially for use in Nabisco for the post-baking process. After the oven, bakery oven, you get spot very wet, moist, another spot very dry, and then you run through the RF a couple of minutes. This RF seek the moist part and evaporate the moisture. So a couple of minutes, you can have a very even moisture content after the RF drying. So it's extensively used in the bakery industry. Now, what's the potential of microwave and RF for sterilization applications? I show here a graph that I noticed that Joseph has used yesterday. Here is the typical, we call it TDT curve, so Modestin curve here for Clostridium botulinum. This is a 12-log reduction curve. So if you expose the spores, Clostridium botulinum spores, in the heated media without any protection, it takes about 2-3 minutes at 121 degrees C to have a 12-log reduction. But if you reduce the temperature to 111, it takes 30 minutes. And you think about the boiling point, the 100 degrees C, you're talking about 300 minutes. That is the equivalent to about over 6 hours. That's what Nicolas Lepault was using. So you can slide along this line, depending upon your application. For liquid product, you can use 131 degrees C for 0.3 minutes to have a 12-log reduction. So that you have a high temperature, short-time process for shelf-stable products. Now, the problem with the can is that because of heat transfer problems, you want to bring the cold spot beyond this line. But the surface of the product already exposed for quite a while, then you have a quality, this part went beyond the quality line, and then you have a heavily damaged product or severely degraded products. And even though your center part is okay. What we're trying to achieve with RF and microwave is that you deliver the energy very uniformly and to the volumetric part of it. And then you take away the energy when the heat is done and adequate. So hopefully we can control this operation region within these two lines, in the boundary of two lines, so that you have a complete control for the Clostridium botulinum spore, and in the meantime, to not damage the products. So that's the promise of the high temperature short-time process, microwave and RF sterilization for solid product. For liquid, you can use heat exchange, a heat exchanger and other means to deliver the energy very easily. But for solid, pre-packaged product, we think we can only use at least microwave and RF to achieve that. Maybe there's other means to do that. High pressure maybe ultra high pressure may be another means to deliver the thermal energy. The challenge of using microwave on RF, the reason why we still do not see extensive application is you need to overcome non-uniform field in RF microcrystallization system. The experience that you have at home is also experience in the industry. If you put a product in the oven, you sometimes see the hot spot and cold spot. If you put a frozen product in the oven, you have to take it out and mix it and put it back again. It's because of the non-uniformity of the oven field. Secondly, especially for shelf-stable products, we do need to develop a reliable procedure to process the products, ensure the safety, number one, and then retain the quality. So I'll give you a kind of short review of what's happening in the industry, in the research area on the microcrystallization, but I'm going to focus mostly on the industry part. All the past industry microcrystallizations they use 2450 frequencies, the short wave that they use at home. So this is the burst-off technology, German technology. What you see is you see the applicator here, just like home applicator. From the bottom and the top is a conveyor belt. This is not a sterilization unit. This is the pasteurization unit. This is not a pressurized chamber. So you can move the prepackaged product through it, and then you randomly heat up the products from the top and the bottom at a certain time. Hopefully you have a safe product, a pasteurized product. This is a sterilized product. Basically, you have a pressurized vessel. Inside the vessel, you have a heating zone, and the holding zone, and then the cooling zone, all in the same large container, pressurized. But this is the early versions of a sterilization unit. We call it OMEC system here. Was adapting the system and used it's a Kobe earthquake at about 94 when Kobe had earthquake. There was no electricity. They used a shelf-stable microwave product and shipped to Kobe for the people to consume. And then Tops Food changed the design of OMEC. That was me when I was younger. That was the year 2000. You look at the plant. I visited the plant from outside. It's like an office building. You don't see much of the chimney and don't see steam coming out. It's just like an office building from outside. Inside, this is the system inside. You don't see a drop of water on the floor. And then 12 people operate the whole industry, a whole plant. They produce about 12 million trays per year, and then now they double that already. So 12 people, including the office people, QA people, the manager, and then 3 or 4 people handling the production, handling the freezing part, and the filling operations. All retort is all automated. So when you look at this, it's wow. This is the industry in the future. I was how do you call that? I basically step into the future about 20, 30 years. People trying to adapt this technology into U.S. The reason they have difficulty is that they use 2450 megahertz frequencies, and then I'm going to talk a little bit later. This is the temperature profiles. They talk about 30 minutes of heating and then cooling. Now you may say that okay, 30 minutes is not much different from what we use for trays in using steam. But the difference is that you look at this. This is the center temperature, and then surface temperature follow almost the same as the center temperature. So therefore, you don't have an overly exposed part of the product that is overly cooked. So these products more or less uniformly heat up for the same profile, able to retain the quality. This is the products that they fit me. I took about 4 hours for me to go through and ask the questions. Then QA people say, Jimmy, what do you want for lunch? I say, what do you have? So they presented me a menu of about 12 different products. 12 are sterilized, and then there's another 12 are pasteurized. So I look at it and I pick up a few, and then about 5 minutes, they took the tray, put it in the microwave oven, and heat it up, and then present to me. I said, well, before I taste them, I took picture of them. Those are the picture. Basically, is the compartment tray. One part is rice and pasta. Another part is sauce and meat. So very nice presented, and it cost about $2.5 dollars at the time. So this is a complete meal. So this is the pasta. You can tell the difference between the pasteurized pasta and the sterilized product. The difference is the compression, because you have to raise the temperature beyond 100 degrees C, and then there's some compression in the texture of it. But other than that, I see some color changes. But nevertheless, this is quite appealing. So the production actually increased quite a bit over the last few years. And they're, I believe, the only one in Belgium that is producing it, and they market it to different countries. The limitation of a 2 for 50 MHz system is a shallow penetration depth, is about 1 centimeter. Multi-mode system, meaning that you have a different kind of hot spot, cold spot, and those modes are not stable. When you have a change of temperature, change of the position, you flip to a different type of mode, and therefore it's difficult to say that this is the cold spot and that is the hot spot. It isn't random. So it makes it very difficult to go through the FDA approval. So this is a demonstrate that this is one of the mode in your oven, and this mode is highly unstable. So once you put the food there, it switches to a totally different mode. And there's about 11 or 14 possibilities, depending upon the size of your cavity. It flips all the time. So it's very difficult for you to find out where is the cold spot, where is the hot spot. Another property associated with the food is we call the Dalledge properties. There are two parts of it. Dalledge constant, that is the storage part of it, and then loss factor is the conversion of electromagnetic energy to the thermal energy. So if this is a zero, you don't have any conversion. For example, if you have a plastic film has very low loss factor in the range that we are using microwave and RF. Therefore, you do not heat it up. For food, this value is about from 3 to 10. Then that gives the conversion. So for oil, this is a 0.00. So by measuring the properties as a function of frequency and the temperature, that gives you idea of if this material heats well or not well. When we design microwave system, we want to choose plastic material as a window to allow microwave to pass through. We want to choose something with very low loss factor, so that itself won't absorb energy. And also in the microwave system we're talking about, I use water. We use water to in combination with microwave to heat the product. Water heats the surface, and the microwave heats the center. The water temperature actually decreases with water loss factor decreases with the temperature. Actually, at 100 degrees C, beyond that, water does not really absorb as much energy as at the room temperature, especially at 915. So we use the property of the direct property dependence on temperature to design our system. There are two parts that contribute to the loss factor. One is the dipole rotation, like water molecules that changes directions as you change the frequency. And then another is the ionic conduction, like omega heating, when the charged particles move around, and then it generates heat. So once the so one is this space charge polarization, another is polarization. So these are the two mechanisms that contribute to the heating, and each play a different role at different frequencies. If you look at the water here, water, because of the size of the water molecules, it generates the maximum heat at 20,000 megahertz. We're catching a tail of 2450 and 915 is at this end. So when you increase the temperature, this peak shift away from our frequency. Therefore, for water, you see a less ability to convert electromagnetic energy to heat at the frequency that we're using. And then if you have a salt in the products, the salt really helps to do the conversion. The higher the temperature, the more conversion it has. So if you look at the frequency, we have a microwave frequency here. We have RF frequency at the lower end. So RF, ionic conductivity contribute quite a bit. And then when you hit the temperature, or hit the product, temperature rises, you have more of a conversion. So you tend to have a similar amount of way. So we have a system here to measure temperature as a function of the loss factor as a function of temperature. Here you can put the test. Different products behave differently as you heat it up. This is the ham because of the ionic conductivity and a lot of salt there. When you heat more, there's more conversion in there, and then we call it thermal runaway. And we usually don't want to see that happening. That really create a problem for you. For most of the product at the 2450, it decreases. So that's good for us. For distilled water, if you look at this, it actually decreases very rapidly as you increase the temperature. So we use that property for our design of system. So this is again what happens in a microwave oven. Agitation of molecules generate heat, and if you have a part that's cold, that may still keep cold because short time. Conduction still to not take the thermal energy there, and therefore you have to use the time to allow the heat conduction to the thermal energy through. One important concept is the penetration depth. All the electromagnetic energy decays when you hit dielectric loss material, and we define a certain reduction point as the penetration depth. That is correspond to about 63% of reduction we define. Different material have different penetration depths at different kind of frequencies. If you look at the RF, the penetration depth, this is a centimeter, is much larger than microwave, and then in the microwave, 915 has a longer penetration depth than 2450. So that's why for thick product we use RF. For thin product, we use 2450, and mostly for industrial application, we use 915. At Washington State, we use 915. What we did was develop a microwave sterilization system for single meals based on 915 technology, and then RF as well. We developed a sterilization system for industrial, for large institutional tray, again, support the U.S. Army Navy Soldier Center. I'm going to spend more time on microwave than RF in the next part of the presentation. For the microwave sterilization, we formed a consortium year 2001 with the help of U.S. Army NATIC and also DOE, Department of Defense dual use project grant. We had packaging company, Rexon Container, graphic packaging, microwave equipment company, Ferret Component, and 4 food companies, Kraft, Hormel, Master Food, and Ocean Beauty Seafood. And then NFPA, Brad Schaeffer has been working with us over the last many years. And then we have always support from U.S. Army Navy Soldier Center, starting from the concept, then from the consortium, and now we're designing a next generation system to go through FDA. So this is the approach we took. We use a computer simulation to guide the design, system design, and then we build a system, and then we use microbial validation to validate the system. And now we are somewhere here scaling up, and FDA approval. This is the pilot plant unit. We have 2 generators on both sides, and then microwave come from top and from bottom, and inside is our pattern cavity and in that box. We also apply water in there so that the food is immersed in the water during the heating, and we use 121 degrees C for the surface heating, and then we use a microwave from top and the bottom of the tray and heat it up. The process took about 10 minutes to have a 3 12 log reduction, minimum 12 log reduction. This is what we did to find a cold spot. We use model food with matching dietetic property as the food that you're processing, like meat, salmon, or other products. And we put ribose in there. This is a technology developed by Natick. It's called chemical marker. And then after the RF heat, microwave heating, then we use imaging to identify cold spot. Then we measure the temperature of the cold spot with fiber optical sensors and then to develop the process. Then we put the real food in there and then confirm the cold spot and then reconfirm the process time, and then we run the food through. Then we do the incubation study, inoculated pack study, incubation study, the process. This is the salmon fillet. We put in the pre-package it and run through the microwave, and it takes about 10 minutes. This is the Epsom 0 of 8 here. Compared to the retort, which takes 77 minutes, the product is quite different. This is a recent study showed the kinetics of the texture changes of a salmon fillet. When it heats up, the texture becomes firm and then drops. And microwave catches this first peak here. This is about 10 minutes. And we call this more collagen kind of softening and degradation. And then after that, the fiber is going to fall apart and then toughened. And then after the peak, then the fiber is also going to softened. So this is the second peak. After the second peak, this is what you see in the retort of salmon fillet. So microwave can take advantage of short time. We can take advantage of that first peak part to have a firm product. We also process the egg product. You can see the difference between the retort, microwave, and this is just a pre-cooked preformed egg before putting into the process as a control. And then we have a mashed potato, a retort. This is the microwave, and this is the control. This is the salmon, again, rice with carrots. You can see the color, and peas. This is sterilized, and then we can put different sauce in the salmons. This is a kind of soy. Also, we look at the packaging. Even though you have a good product, but if you do not have a good package material, the product quality cannot be retained. So over the last year, we also look at the different package materials. And one package material we're very interested in is EVOH film. EVOH film gives you very low permeability if they're not sterilized, not went through the retort. But the problem with EVOH film with conventional retort is that after 30 minutes, water get into the EVOH film through the PP polypropylene layer, and then EVOH film absorbs the moisture and then reduces the permeability. Actually increase permeability, reduce the barrier properties. So we compared the EVOH film with a commercially used PVDC film, and you can tell that for control, you have a much lower permeability with EVOH film than the conventional PVDC film used in the industry. And then, of course, after the microwave, it gains some moisture and then reduces the permeability. actually increase permeability, reduce the barrier property, but still they are much lower than the conventional, commercially used PVDC film. So we think that with the microwave we can use EVOH film, and we are still working with Evoca as a company based in Houston to improve the performance of this. What we are hoping is a 3-year shelf life without using foam. This is what happens with retort. Using the same film, you see these bubbles after the retort. This is 26 minutes. This is 10 minutes. That shows the difference. So microwave short time process really helps retain the quality, not only the product, the package. I presented this last year here, but probably for most audience who have not seen this before, this was done at the U.S. Army Natick Soldier Center. We sent 50 trays chicken there in January of 2004. Then after accelerated shelf life study, this is equivalent to 3 years at 80 degrees Fahrenheit. This is the microwave products, and this is the retorted products, still above 6. So I don't know if Pat is going to talk a little more later on.
I have a slide.
Yeah. Okay. But anyway, so the implication is that about anything above 6 is acceptable, is right? And maybe, yeah, more than acceptable.
9 point in diet, and 9 is light extreme.
Okay.
5 is neither light nor this light, so that's our
So this is the results from Pat's group. Yeah. Yeah. So RF, we also developed pilot plant unit for RF. Again, we use electrodes, and we have pressurized vessel and put product in there. And then we use the polymeric tray that with aluminum. And then you see the RF process compared to the retort process is much shortened. Again, the surface part, this retort severely burned after the retort process. With RF, you see a better quality, better quality. You can put a prepackaged rice, small trays in there as well. We just processed with RF as well. You can see this RF process tray, shelf-stable rice in there. Our target, again, is Clostridium vaginatum spore, and we've been working with the FPA using their crop 3670 gates, and then we validate different product already, mashed potato, salmon fillet, and we are working on sliced beef, and I'm going to report results tomorrow. We are at the early stage of doing that work. There's no result yet. We've been visiting FDA, a couple of times already. This is a meeting September 20th, and then we met last time year. What we're trying to do now, next step is to scale it up for FDA approval. We want to design a semi-continuous system so that each tray is going to expose to the same type of environment, so ensure that we can have a good repeatable process. And then, so hopefully when we're going to approach FDA for approval. So there's some, if you want to learn more about it, here's the website for sterilization. It's very easy to remember, microwaveheating.wsu.edu, and also we have an article on our. With that, thank you very much for your attention.